Alright, this video is on density curves. So density curves are a pretty important part of statistics, and we're going to try my best here to explain every single part of it as we can. So before we actually get into what a density curve is, let's make sure we understand what we've learned so far in exploring quantitative data. So when you're given a set of quantitative data, how do you explore it? So step one is to, anytime you're given a set of data, is you want to graph the data. Now, when we have quantitative data, we know that that could be a stem plot. That could be a box plot. That could be a histogram. That could be a relative histogram. That could be an ogive. That could even be a dot plot. But we want to graph the data. And then what we want to do is the second step is look for overall patterns and shape. So what do you notice about your data? What do you see in the picture? What kind of idea do you get from looking at that picture? And what does the picture tell you about your data? Does it tell you that your data is clustered to the left, or clustered to the right, or clustered in the center, or spread evenly throughout, or clumped in one area and spread throughout the rest? What does the graph tell you about your data? So we've learned about that as well. And the third thing we've done is we've learned that once you kind of have your data, once you got all of your data, you can actually calculate the best values for center and spread. And I say the best values because we talked about data that is nice and symmetric and mound-shaped, and that's when you should use the mean and the standard deviation for your center and spread. And we talked about other types of data that's maybe skewed left or skewed right or has some major outliers. And in that type of data, you'd want to use the median and the IQR to measure your center and spread. But the idea is that we now know ways to calculate center and spread specifically. But there is a new kind of fourth option that we're going to kind of talk about today, obviously with density curves. So sometimes the pattern is so regular. Sometimes the pattern is so regular we can use a smooth curve to represent it. We can use a smooth curve to represent it. And that's the idea here. When you see a pattern in your data that is so regular, so let's just say that I'm looking at weights of a sample of high school teenagers, and I see this pattern, and I get another sample, and I see the same kind of pattern, the same kind of shape, and I get another sample, and I see the same pattern, the same shape. When you start to see such a regular pattern occurring, we can maybe use a smooth curve to kind of represent or approximate that shape. So the best way for me to describe this is with an example. So here's an example of scores on the Iowa test for basic knowledge here. Now, you guys may have actually taken the Iowa test back when you were in 4th grade or 7th grade, or I don't even know what grade they take it. But this data came from a group of 947 students. And you take this Iowa test, which just kind of gives you a vocabulary score. It tells you what your vocabulary is. Now, we see here the purple or light blue or whatever you want to call that color histogram. And that histogram represents the actual data. That histogram is real. That histogram actually came from the data. I know there's no y-axis here, but we could see that clearly a lot of students scored somewhere in the 7 range is where most students scored. Very few students scored down here around 2 or 3, and very few students did really, really well. So we start to see that this is a very, very easy to recognize pattern, and what we could do with such an easy to recognize pattern in our data is we can make a smooth curve, as you see in red here, and we see this smooth curve that kind of goes around the data and really represents the data. Now, it's not perfect. Obviously, there's parts of the curve where our real data went higher than the curve, and there's parts where the real data was lower than the curve. So the curve is just there to represent a regular trend in our data or a regular pattern that we may see in our data. So lots of data First off, what do I mean by a regular distribution? Well, first off, if you only have 5 kids can be all over the place. I want to consider that regular. So for data to be considered regular, you need lots of data. I mean, 947 test scores is really going to start to show a good pattern, as this one clearly does. And we also need data that's consistent. Data that's consistent from one group of fourth graders to another group of fourth graders to a third group of fourth graders to a fifth group of fourth graders. If we see the same kind of general pattern, lots of scores around the 7s, low on around the 2, low around the 12, then we could start to, again, use a density curve, use one of these red curves to kind of simulate maybe or anticipate or predict what our data is going to look like. Once again, it's not always accurate, but we find out is that the data is actually pretty good at predicting. For example, if we talked about anybody that has a score under a 5. So right here's a 5. So if I draw a line straight up, right? If I talk about anybody that has a score under a 5. Now, that would be these marks here, these bins here, right? And if I were to think about all those bins and divide those by the grand total, I would get my proportion of kids that scored below a 5. But what we find out is that if we looked at the area underneath this red line right here, we would get a very similar answer. Yeah, and you may say it doesn't fit perfectly, but notice that sometimes it does go over like here and here, but sometimes it goes under like here and here. So basically it kind of balances out. And if I were to look at the overall area of the purple histogram under a score of 5 and the overall area of the area underneath the red density curve, I would have about the same area. And again, it's not perfect, but sometimes the highs and lows balance each other out. And that's what makes these density curves pretty good at modeling our actual data. So now that we kind of got to see an actual density curve, let's try to write down what a density curve is. So I want this to be pretty clear. A density curve is a curve that. So a density curve is a curve that is always on or above the x-axis. Density curves can't dip down below the and go into the negative x-axis. That doesn't even make any sense. Okay? And the other important aspect of a density curve is a density curve has area exactly 1 underneath it. So when we're talking about a density curve, we're talking about that there's an area of exactly 1 underneath it. And what we mean by 1, we mean is 100% 1, right? 100% of the data falls underneath it. It's not like there's 90% of the data where we don't even know where the other 10% went. No, we know that under a density curve is where all of our data falls. So a density curve describes the overall pattern of a distribution, and the area under represents the data. So a density curve describes the overall pattern of a distribution. So I'm going to write that down as well. Describes the overall pattern of a distribution. And again, I said it's not always going to be perfect, but the idea is that if your pattern is pretty regular, it's going to be pretty good at predicting that data. Now, a couple things to keep in mind here is that density curves, like distributions, come in many shapes. A density curve is often a good description of the overall pattern of a distribution. We've said that several times. Outliers, which are departures from the overall pattern, are not described by a density curve. No set of real data is exactly described perfectly by a density curve. The curve is an approximation that is easy to use and accurate enough for practical use. And that's the idea of a density curve. There's all kinds of density curves out there. There's a lot of really popular ones. There's a lot of kind of unpopular ones. But there's a lot of different density curves out there. But it's important that you understand is that the curve is an approximation that is an easy to use and accurate enough model for practical purposes. So what I wanted to figure out now real quick is I want you to understand that we have real data. When you have real data, you can make a histogram. And when you have that histogram, you could calculate the mean, right? and we know that the symbol for mean is x bar. And you could also calculate the standard deviation. Our symbol for standard deviation is s sub x. Okay, but when you have model data, right, model data, when you're just trying to model what your data looks like, you use a density curve. Now, a model data is like theoretical. It's an approximation. It's not real, like real data would be. It's just a model. So to make sure that we use a different symbol for the mean, we use this symbol mu, and it's literally the Greek letter mu. It's pronounced mu, mu, and it looks like a U that's got this kind of front tail on the front there, okay? Now, mu is used, it means the mean, just like x bar does, but it's to represent the idea that it's not coming from real data. It's just a number that's used to model what the population theoretically could look like. Again, we're never going to know the average weight of all African bullfrogs, for example. There's no way we're going to know. We might know a sample, x bar, we might know a sample mean, but we're never going to know the true mean of all. But we can model what that true mean would look like. In that case, we'd use mu to represent that mean. Standard deviation, same idea. For standard deviation, we use this symbol sigma. It looks like an O with a little tail coming off the top there, and that is read as sigma. And this symbol sigma just represents a theoretical mean, a theoretical standard deviation, from a density curve. Once again, think about African bullfrogs, right? I don't know the average weight of all African bullfrogs, but I could take a sample, and that would give me an x bar, and I could find my sample standard deviation, s of x. But if I wanted to think about a model that would maybe predict all African bullfrogs, all 100% of them, I could think of a density curve. And I could think of mu as the mean that is theoretically true, and standard deviation sigma as what is, again, theoretically true. So make sure you understand those symbols, and these are two different ways to use symbols to represent mean and standard deviation, whether it's coming from real data or coming from modeled data. All right, so let's take a couple examples here, just some basic examples of some density curves. First off, most people think curves, it's got to have curves. Well, no, actually, if your data is very uniform, you could actually have a square like this, right, rectangle. So this example right here is actually a density curve. So this tells me that my data all falls from 2 to 6. There's no way I could be more, no way I could be less. And the fact that it's a perfect rectangle tells me it's very uniform, which means I should see the same amount of data from 2 to 3, and I see the exact same amount of data from 3 to 4, and I see the exact same amount of data from 4 to 5, and I see the exact same amount of data from 5 to 6. Now remember, density curves have an area of 1, so this entire yellow rectangle has an area of 1 underneath it. And if I take 1 and split it up 4 ways, I get a fourth of my data here, a fourth of my data here, a fourth of my data here, or a fourth of my data here, or 0.25, 0.25, 0.25, 0.25. And that's just because it's so perfectly uniform. So don't think it has to be a curve. Now over here's an example of one that is a curve. Obviously we see a slightly skewed right curve here, and this tells me that there's more data from 9 to 10 as opposed to 12 to 13. And again, notice that the area here is much, much bigger than the area over here. So again, it just tells me there's more data falling from 9 to 10, or I'm typically going to get more scores from 9 to 10, or more values, whatever that would be. But again, under that entire yellow curve is 100% of my data, or an area of 1. So this portion over here, I don't know, you could estimate that to be maybe 30%, and this over here might be 10%. Again, you're just estimating right now from looking at a picture, but the idea is that underneath the entire curve is 100% of the data. All right, now I found this cartoon that I thought was kind of funny that kind of fit this, and it's from Foxtrot, and Foxtrot says, Miss O'Malley, in case you were thinking about grading our math tests on a curve, I preferred some templates you might find handy. So maybe you've heard that before, grading the tests on a curve. Now, here's his first example. It says, here's one where everyone fails except for me. So you see that there's two little kind of humps in the curve, one where there's a huge amount of people getting an F, and then there's this smaller curve right here at the A, and that's, of course, him. Or he says, here's one where almost everyone fails except me. So a little bit more skewed to the right. Some kids might get D's and some few get C's, but most kids are going to get F's. But then again, remember, he gets that A down here. And then here's one he says, here's one where the test is so hard everyone quits except for me. So all of the data falls under the A, and all of the data would just be him, because remember, everybody else quit. So I thought that was kind of a cute cartoon that shows that, how density curves, are used and how they should make a lot of sense to you. Alright, so now the first thing we want to talk about, or actually we're almost done with this video, it's a fairly short one, is we just want to talk about describing density curves. And we love describing the mean and the median of curves. So the mean and the median, when you're perfectly symmetric, like here's this blue density curve where we're perfectly symmetric, the mean and the median are the exact same. They fall right in the middle, right? We have a little bit of data on the far left, a little bit of data on the far right, and most of the data right smack dab in the middle. So when we're taking about the mean is looked at as a balance point. So the mean is a balance point. Okay. If the curve was made of a solid material, so it's the balance point. I think I spelled balance wrong. Balance point if curve was solid material. Okay, so if we were to think about this curve right here, we would think, well, it's this solid figure, right? The solid material is perfectly the same on the left as is the right, so the balance point would be right smack dab in the middle. That's the mean. Now the median is the equal areas point. Equal, oh boy, I really spelled that wrong. Equal areas point, meaning that it has the same equal area on the left as it does on the right. So there's the same area on the left as there is on the right, which you notice when you're nice and symmetric like this curve here, again, the mean and the median fall at the same point. However, when you're skewed right like this picture, the median is trying to keep in track 50% of the data on the left and 50% of the data on the right. And that's why, since there's more data on the left, the median is going to go towards that chunk or that cluster on the left-hand side here. However, the mean is trying to keep everybody happy in terms of being a balance point. So it's going to have to go a little bit to the right, and we've talked about this before. When you're skewed right, the mean is going to go a little bit to the right. That way it can balance it out. That way, it has to move that way to get more data over there to keep everything kind of balanced out. So we talked about that in class. Here's an example of a slightly skewed left, and a couple questions I would ask you. Why is this a legitimate density curve? First off, there's two reasons why this is a density curve. Because the total area underneath it is 1, or 100% of the data. The other reason why is that the entire curve is above the x-axis. Those are the two characteristics that make you a density curve. Now again, remember, it can be a rectangle. It doesn't have to be a curve per se. Now another question I could say is, about what proportion of observations lie between 7 and 8? So I even shaded 7 to 8 in this dark green, and we see that there's about 12%, right? You can move that decimal over. About 12% of data falls between 7 and 8. And right now that's just kind of eyeballing. We're going to actually learn how to calculate that exactly later on, but it's just kind of looking at, that shaded area represents about 12% of the data. So we could also try to figure out where's the mean and the median. Now, the median needs 50% on the left and the right, so maybe the median is somewhere around here. But the mean, however, is going to go a little bit to the left to kind of adjust for these values up here that are weighted more. They weigh more. So the mean might fall somewhere right around here. Now, notice the symbol I'm going to use for mean is our new symbol mu, because x bar comes from real data that's in a histogram or a stem plot or a dot plot. But if we're just talking about a density curve that's approximating or theoretical talking about what data could look like, that's where we would actually go ahead and use mu to represent the mean. So remember that idea of real data versus a density curve, which is just trying to model what an overall shape of most data could look like. Okay? Again, if you really want help with this, go back over here real quick. The actual histogram represents a set of 947 kids. That's real data. But what if I had another group of kids, and another group, and another group, and another group, and another group? I would expect all those kids to be very consistent, meaning they would follow this basic red model. Yet, I don't know the mean of all of those kids. I could theoretically think what it's probably going to be somewhere between 6 and 8, probably right around 7 somewhere. But because I don't know that exactly, I would have to call that mean mu. It's just a different symbol to represent a modeled value versus an actual set of data. Okay? Lastly, I just got 4 more examples. Sorry, they're kind of all over the place, but we're just trying to talk about where's the mean and the median. So if we're talking about this one right here, B would probably be my median, and because I'm skewed right, C would be the mean, because it's going to have to go over a little bit. A just looks a little bit too far left. It looks like there's definitely more area to the right of A than there is to the left, and the median needs 50-50. B here would probably be both my median and my mu, or my mean. I'm sorry, use that symbol a little bit more. Obviously, A is way too left, C is way too right to be my medians, and because I'm nice and symmetric here, I would have a mean that falls right smack dab in the middle. Here's another one right here. This one is very nice and symmetric. So again, A right there is going to be exactly where my mean and my median fall. And again, B can't be the median because there's definitely more area to the left of it, and the median needs to have 50% on the left and the right. And here's one that's skewed left. Once again, B's probably going to be my median. C's a little bit too far. It looks like there's a little bit less area on the right of C than there is on the left of C. So I need B there to kind of be my halfway point, 50%, 50%. But because it's skewed to the left, these values down here are going to weigh a little bit more, so A has to move towards them to kind of balance things out. So A would therefore be where my mu is, or my mean. So that's it for density curves. Density curves are pretty easy, pretty basic. Make sure you understand why we have density curves. They're simply meant to model or predict data that is quote unquote regular and very consistent. And they're not necessarily always going to be true, but they're used to help us predict data and think about data that we might not exactly know what it looks like.